Okay, so I should, I sort of rewrote this because this was sort of ugly at the end. What I was trying to say here is that if you let z be equal to plus or minus 4, then this is what you get, which simplifies to this. And if you want to make this into 1, you get this equation, which is clearly an ellipse, right? And then that's the ellipse I drew in purple here. And so if you add this purple ellipse, the horizontal ellipse, to the plane z is equal to 4 and -4, then you get, these pictures here. And of course, the answer, I mean, the entire picture is going to look like this, right? And of course, this extends, forever to the top and the bottom to positive and negative infinity. And so this is like a double bowl, which is called an elliptic hyperboloid of 2 sheets. All right, so I hope this makes sense. Maybe I just drew too much here, but all right, number 6, and we are getting close to the end, but not quite yet. Okay, we have a few more things to draw here. All right, did you figure out what you get when x is equal to 0? You get something on the YZ plane, and so this is, let me go ahead and write this here. Y over 16 minus z squared over 4 is equal to 0, right? Okay, what in the world is this? And you may want to think of that in terms of in this way: z squared over 4 is equal to y squared over 16, right? Remember, one side is equal to 0, so you don't get hyperbolas anymore. So what do you get? Well, z squared, if you multiply both sides by 4, you get y squared over 4. Okay, and so z is equal to plus or minus y over 2. Now remember, you have plus or minus just because that's how the square root works, right? And so, yeah, that's what that is. Now, what is this? If you try to, I mean, these are lines, right? These are 2 lines. So in terms of z and y, okay, again, remember my canvas is like this. I'm drawing on this canvas where x is equal to 0, z is equal to 1/2 y, and z is equal to -1/2 y. These are lines with the slopes 1/2 and -1/2, okay? So that's what the graph looks like. So this is z is equal to y over 2. This is z is equal to -y over 2, right? So that's just 2 straight lines meeting at the origin. When y is equal to 0, what did you get? X squared over 9 minus z squared over 4 is equal to 0. Z squared over 4 is x squared over 9. Just multiply both sides by 4. And so z is equal to plus or minus 2/3 times x. You also get 2 lines intersecting at the origin. This time y is equal to 0, so that's my canvas, the xz plane on which I am to draw this trace. And this time I get 2 straight lines of slope 2/3 and -2/3. So it will be something like this, something like this. It's not a very good drawing here, okay, but you get the point. It is a little more difficult to see as straight lines here. And then finally, when z is equal to 0, what do you get? Well, x squared over, actually you can guess what happens when z is equal to 0 from these 2 traces we just did. Okay, look at this trace and this trace carefully, and you can probably figure out what happens when z is equal to 0, right? So that's what happens. But again, x squared and y squared would be positive for any number except 0, right? So if x or y is non-zero, this will not happen. So the only time this is true is when x and y are both 0. That's this point. That's the only point that the surface crosses with the horizontal line, a horizontal surface, z is equal to 0. In other words, whatever the surface this is, if I slice it on the xy plane right here, if I slice it, just cut it through at the surface, the level surface, then it just meets the plane at one single point, the origin. That's it, right? So for that case, in this situation, you may want to try something else. For instance, you can let z is equal to plus or minus 2, right? Just like we did before. if you don't get what you want, if you don't get any kind of a reasonable geometric shape, you may want to try something different. You can try different traces if you like. So here then you get this x squared over 9 plus y squared over 16 minus z squared, which is going to be 4 over 4, is equal to 0, right? What in the world is this? Well, you figure this out. This looks very much like an ellipse, right? So when z is equal to 2, maybe I'll do a little different color. If z is equal to plus or minus 2, then what you get is an ellipse where in x directions you go 3 units, and in y you go in 4 units. It'll be like this, and down here it'll be like this. Okay, try to put this all together, and I think you can figure out what this thing looks like, right? So there's one single point where everything meets, and of course the answer is it's going to be a double cone. You have to use some imagination here, right? You can call them 2 cones, or you can call it a double cone, doesn't matter. But anyway, if one side is equal to 0, okay, you will see characteristically something like the cone. So this is called a double cone. And the reason you see the cone is because of precisely of this kind of thing. You can move one variable to the other side, take the square root of both sides, you will end up with plus or minus, and you will get a double cone. All right, so I hope you're doing okay. This was our 6th type of conic section, or 6th type of a quadric surface. Number 7, this time we'll have something very unique. Let's see, you get this, minus z is equal to 0. Try to make it simple. Now, the difference between this one and all the other ones before this is that I have a one variable that is not squared, right? And so what happens if one is not squared? And that's an important point, okay? So let's see if you can figure out what that is. Maybe maybe you should pause this and then try to figure out what happens when x is equal to 0, y is equal to 0, and z is equal to 0. All right, let's do it. Right, when x is equal to 0, you have basically z is equal to y squared over 4, right? So what is that? Remember, you're drawing on this canvas called yz plane when x is equal to 0. This is a parabola. Oh, we haven't seen parabolas yet. Why? If z is equal to y squared, you have the standard parabola, but it's multiplied by 1/4. So it'll be a sort of a wide parabola in the in the yz plane when x is equal to 0. Again, this is a slice or the trace or the cross section when you cut the surface at x is equal to 0 with that vertical wall. If y is equal to 0, similarly, z will be x squared over 9. This time, my canvas or the mural, the wall that I'm drawing this on is where y is equal to 0. That yellow sheet of paper or canvas. And then when I mean canvas, I don't mean that course management system we use. Canvas as in the plane or the surface on which an artist draws a piece of art. All right, so x squared over 9, that's also going to be a what? It's a parabola opening upward, but x squared is multiplied by 1/9, so it's even a wider parabola than the one before, okay? And when z is equal to 0, did you figure this out? If z is equal to 0, you basically have x squared over 9 plus y squared over 4 is equal to 0. That just tells me that x and y has to be equal to 0. Again, that's a single point, because if x and y are any positive or negative values, then they will not add up to 0. So let's try again when z is equal to something like 9. Did I want 9? Yeah, 9 is okay. So then you have x squared over 9 plus y squared over 4 is equal to 9. Maybe I should have tried 1. Yeah, let's try 1. Okay, that's easy. All right, so let's say it's 1, okay? Now you know what that is, okay? That's an ellipse, right? And so that ellipse, if I were to draw this ellipse here, again, using a purple, this happens slightly above the origin, right? And then in X direction, you go 3 units, Y direction, you go 2 units. It'll be an ellipse like this. And when X is negative, I mean, when Z is equal to -1, then what? If you replace this by -1, well, that's not gonna work, okay? And it's gonna be an empty set because this side will be positive, okay? So unlike the case of the double cone or elliptic hyperboloid, this time there's nothing on the bottom, okay? And that makes sense because these are parabolas, right? So can you combine all of these things here? I think you can, right? What you get is something like this. There is no other side of it because these are not hyperbolas. Okay, so that's what it looks like. So that's like a bowl, only one, right? So in this case though, what did we have? We didn't have any hyperbolas, okay? Because the two squared terms are added together. There's no subtraction happening. And so what you see is a parabola, and an ellipse, okay? So remember, when you see two of the same kind, you put the oid at the end. So this should be called a paraboloid, okay? A paraboloid. And this last one will be an adjective that modifies that oid. So this will be called an elliptic paraboloid. Cool, huh? Just go back and talk to your friends or family and say, hey, today I drew my first elliptic paraboloid, and see what they say. All right, and finally, and I will promise this is the last one, and it may be the coolest one. I'm going to give you the name afterwards. I'll let you decide what it should be. You know, the naming convention is something we just talked about, so you should be able to figure this out. I'm going to give you an equation. Here is an equation. What's the difference? Okay, last time you had two square terms added together and one term without the square. This time one term is without the square, but there's a subtraction happening. There's a difference between the x squared term and y squared term. All right, do the same kind of thing. This is going to be weird, but let's see if you can draw this last type of quadric surface. And this should conclude section 2.6 once we drew this and name this. All right, go ahead and try. All right, so what did you get? When x is equal to 0, you have z. I mean, I'm just going to write down, you know, you can just move things around, right? So if x is equal to 0, let's move the y squared term to the other side. You have z is equal to y squared over 4. That is a parabola. Remember, your canvas is when x is equal to 0. That looks like this. And so your graph is going to be z is equal to y squared. That's an parabola that opens up, but then you divide it by 4, so that becomes a widened or a wide parabola. When y is equal to 0, you have x squared over 16. What? Well, z is negative x squared over 16, right? Because you move this on the other side here, this will go away, and so on. So this time you get something that you have never seen before. If you cross it with x is equal to 0, the cross section is going to be an upward parabola. And if you cross the surface at y is equal to 0, you get something that goes down. And this is actually even a wider parabola, right? It's a parabola on the surface of y is equal to 0, but z is negative x squared divided by 16, so it'll be a very wide parabola. How are we going to put this together? This is weird, right? So if z is equal to 0, what you get is x squared over 16 is equal to y squared over 4. That looks familiar, right? What is that? Well, x squared is equal to 4y squared, or maybe I should say y squared. Let's multiply this by 4. Okay, this is what you get. And so y is plus or minus x over 2. Right. So I didn't actually draw this one. Here, let me go ahead and do this. I'm going to erase this. If I sketch this, on my XY plane. What are we going to get here? All right. And I'll show you an illustration of this in the next segment, maybe. But this is what you get, right? What is that? Well, it's two straight lines of slope 1/2 and -1/2. Right? Remember, this is the X and this is Y, right? So it'll be something like this and something like that. Okay, this doesn't tell you anything. How do you combine all of these things, right? So another way to look at this is maybe when, try to find something else. When Z is equal to 2, do I want 2? No, let's do 4. Maybe that's easier, okay? Let's do 4, and you can try different numbers here. It doesn't matter. All right, so you have x squared over 16 minus y squared over 4. Plus 4 is equal to 16, right? So what is it that you get? You can do a little manipulation here. Y squared over 4 minus x squared over 16 is equal to 4. Are we okay so far? I just moved these guys to the other side, right? And then swap the order. I can divide everything by 4, and I will get this is equal to 1. What does that look like? All right, so now I'm looking at Z is equal to 4. That's 2, well, let's see. That's 4 units above. It's like this plane here, okay? On this level where Z is equal to 4, what I'm seeing is hyperbola, where in the Y direction you go 4 units and X direction you go 8 units, all right? So this hyperbola, it may be hard to draw this. Maybe I should draw another color here. In the Y direction, you go 4 units. In the X direction, you go 8 units, right? So this will be something like this, and it'll be going in this direction because Y goes first, right? So in other words, the Y-intercept is there, no X-intercept. All right. So you solve the mystery. This is very, very weird. Okay, so I'll tell you the mystery here. What happens here is, let me go ahead and try to color this so that you can see what's happening here. Let's try to use this as my basis here. Okay, so this is what's happening. Maybe that's not a good idea. Okay, maybe I will use this other one, black, as my base curve here, right? So I'm going to use this as my base curve here, right? So this is my wide parabola that opens up. What you saw in blue is basically this, okay? And you can tell as if you change y is equal to some other number k, like 1, 2, 3, or -1, -3, you'll see always a downward parabola, okay? And that's not going to change. So the answer is it's going to look like this. And if you cross this, at Z is equal to 4, for instance, you will see this. It's hard to picture this, but the answer to this question, and I will have another way to make this clear to you in the next video, hopefully, is this, right? And so what is that? Okay, this one is affectionately called, not surprisingly, a saddle, because that is exactly what it looks like. And I don't know if you thought about this, you have saddle, you sit here and think about this. This is called a saddle point. We will be very familiar with this in a couple of chapters later, we'll be studying this. But if you are walking along this blue path, this is the maximum point. But on the other hand, if you are coming down this black path, this is the lowest point. So what is a saddle point? Saddle point is a maximum point in one direction and minimum point in the other direction, or in other directions. Is there anything like this you've seen before? Well, it's surprisingly, these things are like all around us, okay? You just don't think about this. This is called a point of negative curvature, and we'll be studying this more extensively in days to come. But this kind of a quadric surface, this is the last one we studied, is called a saddle. You may still be surprised about the fact that you saw 2 lines here and you saw a hyperbola here, okay? And in fact, if you put a negative value for z, you'll also see a hyperbola, but that hyperbola goes the other way. And it's really complicated if you look at this right now. And because this is such an important surface, I'll try to demonstrate this surface with some photos, homemade photos, okay? But until then, just trust me, this picture is the accurate one. It looks like this, and it's called a saddle, but that's a nickname, all right? So what is this really called? Well, you have a parabola, you have an upside down parabola, you have the right side up parabola, upside down parabola, and this is going to be an hyperbola, right? Something happened when z is equal to 0 that the mathematicians call this the degeneration. So the hyperbola here, it degenerates into two lines right when z is equal to 0. But typically you see for all z values, except for 0, you'll see hyperbolas. And when z is equal to 0, just something happens. It just happens to be a very special singular thing. And hyperbolas degenerate into two lines. But typically you see in hyperbola. So you see hyperbola, parabola, and parabola. So what should we call this? Well, you see two parabolas. So this should be called a paraboloid. But because the other trace will typically be an hyperbola, this is called an hyperbolic paraboloid. Such a cool name, okay? And a hyperbolic paraboloid basically is a saddle. And you can call this saddle if you want, but more technical name is an hyperbolic paraboloid. This, by the way, is a big thing in things like design, architecture, and other forms of art. All right, so I hope you have learned this well. We have one more section to go in this chapter, but learn to do traces in order to draw these quadric surfaces. All right, I will stop at this point.